So I'll talk about is like some sort of a broad story about models of random geometry, and we'll sort of mostly try to sort of see how the fluctuation theory is expected to change as a sort of underlying disorder that drives the geometry sort of changes in terms of correlation structure. So we'll sort of report some recent progress, but I'll also sort of speculate some things, and we'll see. And we'll sort of come back to this picture, which many of you can already guess what this might be, but we'll sort of see eventually what this is. All right, so the broad question, okay, so we'll sort of focus on random geometry eventually, but so a fundamental problem is to understand sort of random interfaces growing sort of when it's driven by some underlying disorder. So that's sort of a very sort of broad problem. And so here there are some snapshots of two sort of natural instances which could be sort of considered as random interfaces. In nature, this is like a front of a growing forest fire, whereas this one on this side is some bacterial colonies. So and the sort of upshot is like if you zoom out, they will look superficially different, but now if you zoom in, then the fluctuation theory is expected to be somewhat universal. And again, this is sort of the broad message. The fluctuations are expected to be governed by a few universal mechanisms, regardless of what the microscopic properties of the individual models are. And this is and depending on what the universal mechanisms are, we will sort of look at different universality classes. Okay, so now sort of we'll sort of focus on one particular example, which can be also thought of as a growth model, which are random metric spaces. And here sort of metric balls naturally form candidates for random growth. You can look at the boundary of growing metric balls, and sort of a very canonical and very easy to state model. So obviously a lot of people here are familiar with LQG, but even a much more basic model is when the underlying disorder is just i.i.d. So you can think of, let's say, your favorite lattice, let's say Z2, and you can now distort every edge on Z2 by, let's say, an i.i.d. uniform variable or something. Okay, and so that obviously changes the length of the edge, which was initially 1 to now this value of the random variable attached to the edge. And now you can look at geodesics, which are shortest paths in this sort of random metric, right? And so this has sort of a pretty long history at this point. So it was introduced by Hammersley and Welch in the 60s as a model of fluid flow. And recently there's been a sort of a very nice sort of survey work by Offinger, Damron, and Hansen, which sort of summarizes some of the developments. So most of the problems still stay open, but there's been some important developments, and this is sort of a good place to review them. And so here is sort of a simulation of how the metric balls grow from the origin as you sort of increase the radius. And so as you can see, like if you zoom out, you see some sort of a limiting shape appearing. And it turns out that this limit shape is going to be convex because of some subadditive considerations, but the shape is going to be a function of the underlying disorder. So if you go from uniform to exponential, if you go from, let's say, uniform variables on the edges to, let's say, exponential variables, then the shape is going to change. However, if you now zoom in near the boundary, the fluctuation theory is expected to be the same regardless of what the variables are. Okay, so this is what I mean by sort of a universality of the underlying fluctuation theory. So actually in this talk, we'll sort of focus on a slightly different but related model, which is known as last passage percolation. And this is a directed variant. So in forced passage percolation, you look at the shortest path between 2 points. Here we will essentially have the same setting. So you're going to have your lattice, you're going to, let's say, equip the vortices or the edges, let's say vortices with some random weights. And instead of looking at the shortest path between 2 points, we're going to look at 2 points which are sort of directed from each other. And we're going to look at the longest path, but also enforce an orientation. So we'll sort of only consider paths that, I'm sure what's going on. Oops.
Maybe motion sensitive.
Yeah.
You're moving too much.
Right, so yeah, so this is my starting point, let's say the origin, and let's say I want to get to NN, and I want to consider all sort of oriented paths which sort of only take north or right steps. And I'll sort of, for each such path, I'll add up the variables appearing along the path. And that's going to be the length of the weight of the path. And then I'm going to look at the geodesic, which is going to be the longest path instead. So this is going to be the energy maximizing path between these two points. All right. And so here are some simulations of, so these are essentially the metric balls, or whatever, the directed metric balls. So you look at the, so these are the level curves of all the points which have the same distance from the origin, let's say. So this is obviously not a distance because you're maximizing, this is some sort of an anti-metric, but these are sort of the level curves. And these are three sort of instances where, let's say, the disorders are slightly different. Here, let's say you have independent uniform variables. So then you see the, so you see some convex shape, and then they're reasonably smooth. Here the underlying variables are still independent, but let's say have heavy tails. So occasionally there will be quite a few large values, and they can lead to some sort of kinks or corners in your limit shape, because some large value can really sort of make the passage time jump very quickly. And this is again like a situation where it's, things are, you can think of, let's say, a log correlated or a branching random walk type underlying disorder. So this is going to be slightly more, it's going to exhibit a bit more bumpiness due to the correlations compared to the i.i.d. setting. Okay, so this is like some simulations. So any questions about the definition of the models? The last passage is just some disorder, and you look at oriented paths, and we are interested in the energy, among other things. Yeah, so the fluctuation theory of this model is expected to be given or determined mostly by the correlation structure of the underlying disorder and the tail behavior. So depending on whether it's heavy-tailed or light-tailed, whether the correlation is long-range or short-range, but not much beyond that. So, and so the goal, in some sense, will be to study instances where the underlying disorder is in some sense critical, and we'll sort of make precise what this means. But even before getting there, let's sort of first review what is sort of expected even in the most vanilla setting where things are all i.i.d. and, let's say, have exponential tails. And already here, most of the picture is still open, and already and it's sort of quite rich. There's a lot of predictions, and some of the central open problems still are open. Central problems are still open. Okay, so the i.i.d. light tail setting is expected to be in what is known as this Kardar-Parisi-Zhang universality class. So what do I mean by that? So the fluctuation theory is expected to be sort of in line with the behavior of this sort of canonical nonlinear stochastic PDE. So again, this is sort of some PDE which sort of drives sort of a height function on an interface with some sort of, here there is some smoothing term like the Laplacian, and this is sort of the nonlinear square of the gradient term, which is sort of prototypical of some of these models, and the random part is here, which is just white noise. Okay, so but back to the discrete model. So what do we expect? So you look at the, so let's say ln is the passage time or the energy of this geodesic between 0, 0 and nn. So just by some subadditivity or superadditivity considerations, you can expect that the passage time should grow linearly in n. So at least the leading order behavior should be constant times n. But now the more interesting things are the fluctuation behavior. So you can ask, like, if you sort of subtract of this sort of law of large numbers term, so if you look at ln minus c times n, so then it should fluctuate as some power of n, and what is that power? So let's call that power chi for the moment. And the other more geometric observable is the transversal fluctuation of the geodesic. So the geodesic is some path going from origin to nn, and so you can sort of see how much it deviates from the straight line joining the endpoints. So if the path was just a simple random walk, then this would be like square root n. But here this is some extremal path which is maximizing the energy. So it's of interest to understand what the exponent driving its fluctuation is. And it turns out that there is expected that there is some KPZ scaling relation which sort of connects the two. So the fluctuation exponent for the energy and the exponent for the path. So this is usually known as the wandering exponent, and this is the fluctuation exponent. And what is sort of expected is this sort of KPZ relation which says that the fluctuation exponent is twice the wandering exponent minus 1. And it turns out that in this sort of KPZ equation sort of situation where it's d equal to 2, so you're in the plane, so obviously this model makes sense in any dimension, but let's say if you're on the plane, then it's expected that the fluctuation exponent is 1/3. So you see that this is less than 1/2, right? So if you look at a single fixed path, the energy of that path is just a sum of independent random variables. So its fluctuation is square root n. And here we are looking at the maximum over all paths, so that's expected to be more concentrated. And so that's sort of reflected in the fact that this exponent is smaller than 1/2. And the corresponding wandering exponent for the path is supposed to be 2/3, which is more than root n, so the path actually deviates a bit more than a typical path in order to gather like large weighted random variables. Okay? So is this setting roughly clear? Okay. And okay, so where do these exponents 1/3 and 2/3 come from? So it turns out that there is a sort of, it can be expressed like in a rather sort of geometric term, which is like there is some underlying competition between sort of a Brownian fluctuation behavior due to the i.i.d. nature of the underlying disorder, competing with some parabolic curvature coming from this sort of convex body that I indicated. So let's see, so suppose I want to understand where the geodesic passes through. Let's say in the middle line. So the geodesic was starting from 0, 0, and let's say it ends at nn. And let's say I'm interested in where it sort of intersects the middle anti-diagonal. Okay, so what I can do is I can try to sort of plot the distance function on this line from the origin. And then the geodesic will sort of roughly go through the place where the distance function is maximized. Right? Because the geodesic is length maximizing. So the distance function has two components. One is sort of a deterministic component, which is coming from this kind of convex limit shape that I indicated in the figure. So that looks roughly like a parabola. And then on top of that, there is some fluctuation which is roughly Brownian in nature. So basically the location through which the geodesic passes is given by a maximization problem where you have this parabolic part, and it turns out that the 1/n comes from the sort of scale of the problem. So it's minus x squared by n is the sort of deterministic parabolic part, and square root x is roughly the Brownian fluctuation on top of that. And so you want to sort of take this to, so this is sort of the competition that I was alluding to. So a parabolic curvature with some Brownian fluctuation. And you want to sort of see where this is maximized. And if you just do some basic calculus, you will see that this is sort of roughly maximized at x equal to n to the 2/3. So the geodesic fluctuates by n to the 2/3 because it's trying to maximize a random function which is like a parabola plus a Brownian motion. And obviously at that point the fluctuation is going to be still given by square root of x, which is n to the 1/3. Okay, so this is the source of these two exponents on the plane. And so such predictions are still pretty much broadly open, but have been proven in a class of exactly solvable models. So we'll sort of not talk about that. So this is sort of the thing that you expect when things are all i.i.d. But we'll sort of instead focus on a class of models where you don't expect the K-pieces theory to hold. And so this is sort of, we'll sort of slowly sort of move into a precise setting, but like roughly what you should keep in mind is like you're going to look at models when the underlying disorder has some sort of a hierarchical decomposition into different scales, much as what you sort of see in things like Gaussian Free Field. And yeah, so a canonical class of examples includes the luck-related Gaussian processes like two-dimensional Gaussian Free Field. Okay, so again to motivate, let's sort of look at a still i.i.d. but heavy tail setting. So instead of looking at, let's say, exponential variables or uniform variables, let's say you have still an i.i.d. sort of disorder environment, but where the random variables are heavy tailed in the sense that the probability that a single random variable is bigger than t decays like, let's say, 1/2 to the alpha for some alpha. Okay, and so the K-piece exponents are not supposed to hold in this setting, and so there is some, again, this is all open, but like there is some physics non-rigorous argument that let's sort of go over that to get some sense of what one might expect. So here also the K-piece scaling relation is expected to hold. The fluctuation exponent chi is supposed to be 2 times the wandering exponent minus 1, but the exponents are not going to be 1/3 and 2/3 anymore. So what is expected to be the case is like, let's say the wandering exponent is n to the xi, where xi is some now function of alpha. The alpha is the tail behavior. So the basic argument is saying that the fluctuation is expected to be governed by the largest random variable that you see in this strip. So if the geodesic moves by n to the xi, so then the path, so that the region that is sort of in action is some strip, and the heavy tail nature of the underlying disorder makes some of the values in that strip pretty large. And the main sort of heuristic here, which is sort of the story argument, says that the fluctuation theory is essentially dominated by the largest random variable that you see in that strip. And so it's not very hard to sort of see that the largest random variable that you see in that strip is n to the this number, because the volume of this strip is n to the 1 plus xi. the tail is alpha. So you do some algebra, and this is so if you take this as your fluctuation exponent and also take this KPZ scaling on fate, then you can do some basic algebra to see that the two exponents xi and psi are these two functions of alpha. Okay. And then you can then plug in alpha equal to 5 to see that when alpha is 5, you get the 2/3 and 1/3 back, which is the KPZ thing that I just did a few slides back. So somehow what this indicates is that as alpha sort of ranges from, let's say, 0 to 5, you get a bunch of exponents, and then from alpha 5 onwards, you are back to the KPZ regime. But one thing to note is like this is the wandering exponent, but the path is directed, so the path cannot move by more than n, right?
The heuristic was that you still accepted the
KPZ scaling relation is
scaling relation.
Yeah, but it's not going to be true throughout, so I'm going to just comment on that. But yeah, the basic heuristic is that at least there is some regime where you have the largest weight dominating the fluctuation and also the KPZ scaling relation to be true.
Well, why do you expect at this stage the KPZ scaling relation to be?
The KPZ scaling relation is coming from the fact that so suppose you wander out by n to the xi. So the KPZ scaling relation is built on the fact that the limit shape is convex, and if you go out a bit of a distance, you sort of incur some parabolic loss. So let's say you go out by n to the xi, then the parabolic loss is going to be n to the 2xi minus 1, and the amount that you sort of lose in the parabolic curvature should exactly be your fluctuation, because somehow that's really where the fluctuation of the system and the parabolic loss should be on the same footing. So the KPZ scaling relation is given by the fact that you have some parabolic limit shape, and if you go out by some distance, you incur some parabolic loss, but the amount that you lose in the through the parabolic curvature should exactly match the fluctuation of the system. So n to the 2xi minus 1 is the parabolic loss, and n to the chi is the fluctuation of the system. So these two things should be on the same footing.
Okay, so in some sense, that scaling relation is something you expect as soon as you have a limit shape.
Yeah, exactly. Yeah. So this is just the point that I'm about to make. So xi is also less equal to 1 because it's an n by n box, so you obviously cannot move out by more than n. So xi is less than 1, so if you plug this in, this sort of forces some constraint on alpha, which alpha cannot be very close to 0. Alpha has to be less equal to 2. And so indeed, if alpha is less than 2, you don't have a limit shape. So what will happen is like literally the largest weight in the box will govern everything. So the largest weight is like n to the 2 over alpha. So you will not have any concentration. So the passage time is going to be some random variable at that scale. Okay, so yeah.
I didn't understand what you said about why is it smaller than 1?
Because it's
you're looking at maximum, right?
So xi is the wandering exponent of the path. So it's an n by n box, so it cannot move by more than n.
Sorry.
Yeah, so if alpha is less than 2, then this is not very hard to show that the largest few weights will dominate everything. And this was already done by Hamley and Martin. And so indeed this Flory argument is sort of only true, should be true only in the regime from 2 to 5. Okay.
There's a typo right here. It's the above canonical
Alpha is larger than
greater
2.
than 2, right?
Right.
Just to be sure to understand.
No, when alpha is less than 2, right? So when alpha is close to 0, it's bigger, the tail is heavier.
But your middle line rules out everything but 2 then.
Oh, you mean this line?
Yeah, that should be alpha larger.
Yeah, this one is alpha larger than.
Okay.
Yeah, exactly. Sorry. Yeah.
Left.
Right. So now let's look at the critical alpha equal to 2 case, where you should see some transition. And so, as you can imagine that at this point, like the noise admits some multi-scale structure. And so to see this, like you have your space is 0n squared, and you can tessellate that into boxes of size 2 to the k by 2 to the k. And in each box, the largest weights are typically of size 2 to the k with order 1 many of them. If you look at the critical case where the alpha is equal to 2, then in a 2 to the k by 2 to the k box, the maximum that you will typically see is of size 2 to the k. And there's going to be like some order 1 many of them in some Poisson fashion. So you can think of values of scale 2 to the k as a Poisson point process in your entire box of density like 1 by 2 to the 2k. right? Okay, there are many exponents floating around, but roughly this is the picture that at alpha equal to 2, you can look at all your variables and you can look at their weights in dyadic scales. And for each scale, it's roughly a Poisson process with some intensity. And so the entire noise field should be thought of as like a superposition of log n many different Poisson point processes, one for each scale. And the kth Poisson point process, each vortex, each variable is actually of size 2 to the k. Okay, so this is how you have decomposed your entire noise field. And so from the Fourier argument, it seems like the alpha equal to 2 case is a transition point for the Kibitz relation to hold, as we just discussed. And the passage time should also sort of should transition from being concentrated to non-concentrated. As we saw, like if alpha was less than 2, the largest weight dictates everything, and so it's a random variable at that scale, so it's not concentrated anymore. And when alpha is bigger than 2, the KPZ relation holds, and so there's some concentration, so there should really be some transition also from the concentration perspective. Okay. And okay, so as is sort of already evident, there is some connection to think. Okay, so we had like a bunch of Poisson point processes, but you can sort of another sort of natural hierarchical model is when you look at the branching random walk. So this is stolen from Marek's paper, maybe. Okay, my student stole it. So I don't remember which paper it's.
I'll come after you.
So okay, so this is another sort of hierarchical model where let's say you now take a 2 to the k by 2 to the k box, and instead of having one point with a large value, each of the points have the same value, which is let's say a Gaussian or something. Right? These are somehow related, right? So in the Poisson point process picture, in a given box there was an order 1 number of points, each of whose size was 2 to the k. Whereas here in a 2 to the k by 2 to the k box, every vortex has the same value. And so in some sense a path picks up an equivalent amount of energy if it spends time in that box. So these are somehow connected settings. And okay, so I'll just commit it to perhaps everybody in the audience. So BRW is a Gaussian process, so we'll sort of work with the branching random walk instead of the Gaussian Free Field to make things slightly simpler. And so for each layer you have like some i.i.d. Gaussian per box, and then you sort of add the Gaussians up along the vertices of a tree. You get the final sort of Gaussian process at the bottom. Okay, so these are roughly 2 related hierarchical noise models that will try to understand how this LPP model behaves on. Okay, so again, like a bit of motivation, not particularly relevant for this audience or super experts in this, like LPP and the Gaussian Free Field. So recently there's been a lot of progress in understanding Liouville quantum gravity metric and also pre-limiting models, which are like Liouville force passage percolation, which could be thought of FPP now driven by exponential of the Gaussian Free Field. And a natural LPP analog of this sort of pre-limiting model should sort of converge to some directed version of the LQG metric. Although it's not clear what that is and how to make sense of that yet. And LPP on the Gaussian Free Field should be thought of as a very high temperature model for directed LQG, right? So you have exponential of the Gaussian Free Field with some gamma parameter. Now think of gamma as very, very close to 0. Then you can linearize the exponential. So somehow then it becomes roughly like just an LPP problem on the GFF itself instead of the exponential of the GFF. Okay. Again, these are super speculative, but some connections. And I think LPP and FPP are generally expected to be quite different in such sort of correlated settings, because the directedness constraint can really sort of force some lack of regularity in the metric. If there is some high thick points at some location, for FPP it does not matter where you start from, but for LPP maybe one of them is accessible from one point but not from the other points. Okay, so you should expect some differences in the two models. Unlike in KP's universality, when things were all i.i.d, both LPP and FPP are expected to have this 1/3 and 2/3 exponents, and the basic theory is supposed to be the same. Okay, and so what do we expect for such models which have this sort of hierarchical structure? So you should expect the energy of the geodesic to come from all this logarithmically many scales. So all of these scales should sort of be in action, and that should lead to sort of new logarithmic correction terms. So in particular, remember that we said for KP's universality the growth of the passage time was linear in n by some subadditivity or superadditivity considerations. Here you should expect some polylog corrections to show up with some exponent. The fluctuation theory should, remember, like, so think of alpha as less than 2, then we said nothing is concentrated. So the fluctuation is the same as the energy itself, so it's n to the 2 over alpha. So when alpha is 2, n to the 2 over alpha is n. But because of this sort of hierarchical structure, you also expect some polynomial corrections to appear in the fluctuation theory. And similarly with the transversal fluctuation. So all of these things should have polynomial correction terms with critical exponents. And it turns out because these are logs, it's very hard to simulate them. So in physics, even in the physics literature, there are some experimental studies, but there are no sort of concrete predictions about what these exponents ought to be. Okay. But why is this sort of why is there some hope that this is even analyzable? And the main sort of broad sort of approach is that, okay, so each layer is i.i.d. So it's either Poisson process or some i.i.d. Gaussian field. So this should be sort of in the KPZ universality regime. And then you can sort of maybe hope to sort of use KPZ ideas per scale and then do some multi-scale analysis to patch things together. So that's roughly the broad sort of technical hope. That your understanding about i.i.d. models patched up using multi-scale analysis can give you some insight about these hierarchical models. Okay? And okay, so this is what I meant by that. So let's say this is this sort of Poisson, superposition of Poisson process noise. And this is like a multi-scale decomposition of the geodesic. So the geodesic is sort of maybe this blue pad that is microscopic. And the different colors keep track of the skeletons of the geodesic looked at only at points which are of a particular scale. So the blue path is the actual geodesic, and let's see if I looked at the restriction of the blue path only through points which have the largest value, then it will be this, the red skeleton. And then if you look at finer and finer weights, you sort of get finer and finer skeletons of the geodesic, eventually ending with the actual geodesic. Is it clear what this picture is doing? So you have this 2 to the k for different k weights, and so the geodesic passes through a bunch of them. And you will sort of look at all the points in the geodesic which have a particular weight, let's say 2 to the k, and that's your kth skeleton, or bigger than equal to 2 to the k. So that's your kth skeleton. So if k is, okay, so here maybe it's sort of reverse, but as you sort of allow more and more values, you eventually get the full geodesic, and all the prelimiting ones are certain skeletons at different scales.
Just to be sure, you are talking at points that are bigger than 2 to the k
in
every scale, and do you keep the information of what are the values, or you just say there is one point here that is bigger than 2 to the k?
I mean, in this simulation, it's just like you look at the geodesic, it's a path of length n maybe,
okay.
And then among them you look at all the vertices which are of size bigger than 2 to the k. Now look at the piecewise linear path that passes through those points, and that's your skeleton.
Okay. So it's not like you are doing last passage percolation at every scale, and then you are keeping some.
No, this is like you do last passage percolation on a global noise where everything is there. And then given the geodesic, you have a skeleton decomposition, which is by keeping track of the piecewise linear function passing through the large points on the geodesic. Right?
So you could, so there was like the first point that you picked in the red line. You could actually abandon this later. That's what you're telling me.
No, so this is like the full geodesic is given to you. Let's say you have.
So this is like coarse grain.
Yeah, exactly.
Coarse grain, the actual geodesic.
Yeah. So the blue path is the actual geodesic, and these are the skeletons at different scales here. Yeah. But indeed, so I'll come to,
That's when you build it the other way. That's when you try to
that's actually what the proof will do. But yeah, this is like, because we don't have access to the full geodesic yet. But if I were to give you the full geodesic, you can get a skeleton decomposition of this kind, right? All right. So, okay, what is a trivial upper bound of the passage time? So it's an n log n, right? Because there are log n many layers. Each of them is like KPZ. So each layer contributes no more than some constant times n. And in the best possible scenario, your global geodesic was also a geodesic per scale, which is, I guess, what Marek was briefly alluding to. So obviously that's an upper bound. So your length of your geodesic is at most the length of the geodesic per scale added up. And per scale, the energy is no more than n, from what we just said, and there are log n many layers, and so then it's at most n log n. It's even easier to sort of argue this in the branching random walk case, where the maximum of the field itself is like log n. Right? So the maximum of the field is at most log n, and there are n vertices on any path, so the energy cannot be more than n log n. Right? So the n log n bound is sort of trivial. Okay, so any questions about this? Okay, so some lower bounds. And so this is with Victor Ginsburg, who's one of my students currently at Berkeley, and Kyeongsik, who's was a former student at Berkeley and is now back in Korea. Okay, so let's not, yeah, so with high probability, for the Poisson model, the passage time is at least n times log into the 3/4, up to some log correction that we can ignore for the moment. So, and for the BRW, the lower one that we have is like square root log n. So square root log n is the typical height of the field, but it appears with both positive and negative signs. Here we are maximizing, so you can actually sort of make sure that you pick up positive parts. And so that's sort of, that's roughly the lower bound result. Okay, so n log n is trivial in upper bound for both models. For the Poisson model, obviously you can see that the Poisson model, there is a bit more advantage because there are these high valued points. So if you pass through them, you can sort of make a lot of gain. And also there is no negative cancellation. So in some sense, it's easier to construct lower bounds in this positive non-negative field than the branching random walk. Okay, so is the statement roughly clear?
So I expect it to be the same? Do you expect them to be the same?
I'm not sure. I'm tempted to say, okay, I'm not willing to commit yet, but I'm tempted to say that these are sharp. Not sure. Yeah, okay. So anyhow, so I think it will be quite difficult. So I wouldn't be surprised if these are sharp. Okay, and some for the concentration results. So if you look at the passage time minus its expectation and divide by n, then it turns out to be tight in both the models. So this does not quite claim that this is the right order of fluctuation. It sort of just says that the fluctuation is no more than n. And because we already proved that the typical behavior is like n times polylog, it's either n times, at least n times log into the 3/4 or n times root log n. If you prove an upper bound of n on the fluctuation, that already proves that it's concentrated. And so this proves that at least for the Poisson model at alpha equal to 2, it's concentrated. Whereas for alpha less than 2, it was not concentrated and the whole thing scaled like n to the 2 over alpha. Okay? Questions about the statements here? Yeah.
Would there be another route to a super concentration by the multiple valley type of things?
Yeah, so okay, so in the branching random walk example, okay, one has to be a bit careful, but okay, so for the branching random walk example, this turns out to be already sharp. So this is an upper bound currently, right? But for the branching random walk, the top layer itself is contributing a constant to every vertex, right? So that's already like just a fluctuation in the top layer of the tree is already going to move the geodesic length by order n. So although I don't expect this concentration to be sharp for the Poisson model, for the branching random walk or the Gaussian free field, I expect linear in n to be the, like this already proves that linear in n is the right fluctuation order. Now, whether you can get like, so what is an upper bound? Yeah, good.
I missed that explanation again.
Sorry.
Can you repeat the explanation? Because
For the branch.
I would think it would be square root n.
No. So the passage time is like you're taking branching random walk and you're adding that to f. So now you're adding up vertices of the path, right? So there are n vertices on any given path.
Yes.
And each of them are sharing the top layer of the branching random walk. So the contribution to any path from the top layer of the tree is n times the value of the root.
Okay, that's what you meant. Okay.
Right? And so that's already sort of gives you an n movement, and this is proving that that's actually,
Thanks.
Yeah, for super concentration, okay, so this is, okay, one has to, I'm not sure, so maybe one can look at the overlap of two geodesics or something, that's how you should usually get, but that's not, I don't know. Like this proof goes, I will not present the proof, but this is going via sort of reference time type arguments. But okay, so yeah, so this is the comment that I made, which is for PRW, it has theta n fluctuations because the Doppler alone moves ln by constant times n. And so that coupled with the previous result tells you that indeed this is the right scale for the fluctuation. Yeah, but for the Poisson model, for the heavy-tailed model at alpha equal to 2, I expect the fluctuation to be actually smaller than n by a polylog factor. Although the proof gives you n, and that's already concentration, but the true scale should be n over polylog. And the reason is that, okay, so even in the sort of this Poisson model, there is one vertex or an order 1 number of vertices which are of size n. But they are too far away. The path will actually not venture out that much to pick up those points. So it will sort of so in the region where it moves, the largest value that it will see is actually indeed going to be n over polylog, not n. Okay. Okay, so strategy for lower bounds, I'll sort of, so there's a few more things to cover, but let me just sort of quickly go over the broad strategy for the lower bound. So, and this is sort of going back to Mark's point, so we don't have access to the geodesic. So if you want to prove lower bounds, it suffices to construct some path which has pretty high energy. And so there we can be we can decide whether to pick up a large value now or sort of leave that aside to gain later. And so, okay, so this is going to be a multi-scale construction where we'll specify the geodesic one scale at a time. So we'll specify what the geodesic should do at skeleton k, and then given that skeleton, we'll sort of see what we can do at scale k plus 1. So we'll reveal the Poisson noise one by one, and then sort of eventually we'll end with some candidate path which has high energy. Okay, so that's roughly the strategy. So again, like we'll just do 2 steps of this process. So let's say first initially you have some Poisson process of scale intensity 1. So you can decide what to do. We'll sort of see what dictates this decision. But let's say I sort of pick some points through which my skeleton will pass through. And so I forget about everything else. Then I reveal to you a new Poisson point process whose intensity is a bit bigger by a factor of 4 because it's 2 square, but the weights of each point has become smaller, right? That was the model. And because I've already specified that these are the points through which my skeleton should pass through, the disorder outside these blue boxes don't play any role because I cannot have a directed path which passes through some point here and also passes through the blue points. So just the specification of the skeleton at the previous scale tells me that the only thing that matters in the next scale are these sort of boxes and the Poisson process in these boxes. Okay, so then I'll decide what to do at that scale and then iterate. Okay, so what governs these decisions? So let's say I fix these blue points through which my geodesic passes. Okay, so then I have some Poisson point process inside each box. And so here is a basic fact. Suppose I go from 0, 0 to xy in a Poisson field of intensity lambda, then the number of points that I can pick up in any increasing path is at most square root of xy times lambda. And this is some scale invariant thing. This is basically connected to the fact that if you take a random permutation of size n, the longest increasing subsequence is square root n, or up to some constant. So if you go from 0, 0 to xy, and you have some Poisson process of size lambda, then this is roughly like a random permutation. And if you look at the best oriented path, this is roughly like the longest increasing subsequence in a permutation of size lambda times xy. So you do the square root. So which means that if I specify the skeleton points xi, yi, then the best that I can do from the next scale is essentially this sum, right? For each box, I pick up some square root of the intensity 4 times the volume of this box, and then I add up the boxes. The input being that for each box, this is the upper bound, which is just the fact that this is just this longest increasing problem that I just mentioned. Okay. Okay, so but the simple Cauchy-Schwarz tells us that this square root of this product is no more than n, right? Because these guys all add up to n on the two sides. So, and the equality holds only when these guys are all the same, right? So the Cauchy-Schwarz is tight if all the xi is equal to yi's. So what does this tell us? Somehow tells us that deviating from the diagonal, if the skeleton deviated from the diagonal in the previous scale, you lose in the next scale. Right? Because the xi's and the yi's are the skeletons from the previous scale. So if you deviated too much from the diagonal, then you would lose in the next scale. However, if you keep your xi's and yi's to be very close to the diagonal, then obviously you will not pick up too many Poisson points, because Poisson points are also sort of, there is some entropy, like they're not going to be very close to the diagonal. So if you want, so some deviation is required to get contribution from the current scale, right? So if I deviate too much, I lose in the next scale. If I don't deviate much, I don't pick up too much in the current scale. So there is some trade-off happening. And one way to address this trade-off is to sort of enforce some slope. So instead of, so we can enforce that the skeletons that we are specifying should have slope which is not too much away from 1. So 1 is the diagonal line, so we want to stay somewhat close to the diagonal but not super close. And so this is a kind of a constraint that you can put in, that your point, the skeleton points, so piecewise segments that you see in your skeleton have all slopes which are quite close to 1, like 1 plus minus delta for some delta that you will have to choose. And okay, so then you can do some Taylor expansion, and then you can get something. Okay, so let's not stare too much at this, but okay, it is something. And it turns out that if you sort of impose this delta constraint, that at the kth scale, the slope of the line segments of the skeleton will be 1 minus delta to the k, because you're doing this iteratively. And there are log n many scales, so if you want to pick up some reasonable contribution from all the scales, you should choose your delta to be like 1 by log n, because that's when this thing is order 1 regardless of which scale you're at. Okay, so this is one sort of consideration. So given this, you still have to understand exactly how much points you can pick up if you stay close to the diagonal. So this is like a thin cylinder problem, right? So if I tell you that I'm always within 1 plus delta slope away from the diagonal, what is the maximum passage time I can pick up from any scale? Again, I don't want to dwell too much on this, but you can sort of convince yourself that you can try to divide the thing around the diagonal into rectangles of width square root delta and height 1 by root delta. So the slope is like 1 plus delta or something. So it's not super important.
Sorry, so there's something of the unique I'm not getting. So essentially you are asking me to go into a direction in the big scales?
For every scale, like locally, we are trying to sort of say that, this is scale invariant, right?
Yes, but at the largest scale, you are doing 1 minus...
1 plus minus delta, let's say.
But delta is 1 by log n.
Yeah.
So at the first scale, you're going really, really straight in the diagonal.
Yeah.
But somehow, then your Poisson point process picture would not be satisfied, no? Because like your points are all far away from this diagonal.
Yeah, so one has to be a bit careful. So indeed, you can sort of, if you look at these boxes still have volume 1, right? The root delta by 1 by root delta, this cylinder is thin but has volume 1. So you will still see an order 1 number of Poisson points in this box. So you can pick those up.
I see.
So this is like really the critical scale at which you sort of satisfy the slope constraint, and also you have some points. Right, so this is the tessellation that sort of indeed ensures that you pick up some points.
Thank you.
Okay, anyhow, so again, not too much, let's not go too much into this. And so you can sort of convince yourself that for each cylinder you can pick up order 1 many points. There are n times root delta many cylinders. So overall passage time is n root delta. And you can do that log n many times. So it's roughly like n times log n times root delta, and delta was 1 by log n. So overall you get n root log n lower bound. But remember that we claimed a lower bound which was more than n root log n, it was n times log n to the 3/4. And so it turns out that indeed this, whatever Taylor expansion we did was not optimal. There is still some further cancellation that you can take advantage of to actually take delta to be not 1 by log n, but delta to be 1 by root log n. So there is a bit more that you can do, and that indeed will give you this n to the log n to the 3/4. Okay, so I'm like, okay, so this is hard to sort of convey everything in a talk, but like roughly the message is there is some trade-off going on, how much you want to deviate away from the diagonal and still sort of be able to pick up reasonable amount of points, and it turns out that choosing the slope to be like 1 by root log n is what gives us this lower bound of n to the log n, n times log n to the 3/4. Okay, so let me quickly talk about an application. So again, back to this original LPP problem. But instead of looking at i.i.d. weights which are exponential tails or uniform, let's just keep the disorder arbitrary. So just an i.i.d. field. And it's an important question which has seen some activity about what is the distribution, like what is the condition of the distribution of these i.i.d. variables, which implies that the growth is like at most order n. Right, so we said that the growth is like constant times n, but the constant could become infinity if the variables are heavy-tailed or something. So what is the condition on the i.i.d. distribution which tells you that the growth of the passage time is actually like some constant times n and not superlinear? And so this sort of goes back to work of Cox, Gandolfi, Griffin, and Keston, who proved that if this is known as time constant, this ln over n, the growth rate of the passage time is known as time constant. So what they proved was time constant being finite implies that the individual variables must have finite second moment. And then subsequently, James Martin proved that this condition, which is roughly like a finiteness of the second moment, because you see that if you have finite second moment, the tail should be like 1 by t squared, right? Slightly more than that. And so square root of 1 by t squared is 1 by t, so that's not integrable. So if you do slightly more than that, then this becomes integrable. So these two conditions are not completely unrelated. And so what Martin proved was this condition was enough to imply finiteness of the time constant. And then the question obviously is that is there a sort of a characterization of the distribution which implies finiteness of the time constant? And it hasn't seen any progress since, and it turns out that this lower bound construction allows us to construct a random variable with finite second moment, but infinite time constant. This sort of a multi-scale construction will indeed allow you to construct such a random variable. And the only point that I want to make is that this n root log n lower bound, which I sort of initially presented, which did not capture the cancellations, would not have sufficed for this construction. So the lower bound construction, which had n times log n to the 3/4, in particular slightly more than 1/2, was crucial in constructing a random variable for which the second moment finite, but the time constant still blows up. Okay, anyhow, so that's another sort of application of this lower bound construction. Okay, and then for branching random walk, we proved this n root log n lower bound, and again the construction is some multi-scale. You sort of take these two different routes, you see which one has a higher Gaussian values or the Gaussian sum, and then you alternate per scale. So again, I don't want to go too much into this, but the point is like this long range correlation and the negative weights make the lower bound slightly smaller. And again, it's interesting to see what the truth is. And there are, again, you can do all of this in any dimension, and there are high dimensional versions of our results, which I'm not going to talk about. Okay, so let's, in the remaining time, let me comment a bit on the upper bound. So, as I said, like, so for the branching random walk, it's known that the maximum of the field is log n, actually much more is known, so the last passage time is no more than order n log n. And, okay, so when would this be sharp? Like, when would you sort of expect this to be sharp? So for instance, if you look at the set of thick points where the values are comparable to log n, and if, let's say that set of thick points, this is not true, but let's say the set of thick points oriented percolates. So suppose you have an oriented path which completely lives on the set of thick points, then obviously you will find a path whose value is n times log n, right? Because each of the point on the path is at least log n or some constant times log n, and then you have n of them. Okay, so then the question is, does the set of thick points oriented percolate? And okay, so this is obviously at this point sort of understood, but also let me sort of build up the story. So an easier setting is fractal percolation, where instead of looking at the thick points, you look at sort of a intersection of a bunch of hierarchical percolation models. So this is pick a parameter p, and then for each layer, keep each box with probability p, and then so a particular vortex at the very end survives only when all of its precursor boxes have survived. Okay, so this is some sort of a proxy for the thick point set. So here is this picture. So you take a box, you divide it into 4 boxes, each of them independently decide whether you want to keep it or not. If something gets kept at a particular scale, then you subdivide it further and then repeat. Eventually you end with some subset of the square. And this is sort of a proxy for thick points, because if you, okay, what is a thick point? So it's a point on the branching random walk whose value is like comparable to alpha log, some constant times log n. And one way that this happens is so there are log n many parents, right? So one way that the value at the end is like log n is if the Gaussians along the geodesic is consistently large, right? And so obviously that's independent, and so that happens. So that's exactly this sort of connection to the fractal percolation model, right? So the probability of a particular point being large, if you take that to be p, so the probability of a Gaussian being bigger than alpha is, let's say, p. Then if all of the Gaussians are bigger than alpha, then eventually the size will be bigger than alpha log n. So that's one mechanism to get a thick point. Obviously that's not everything, so that's why this is like a proxy toy version for the geometry of thick points, right? Is this clear why this is sort of a relevant thing to thick points? Okay, so connectivity properties of fractal percolation has been widely studied. So it turns out that there is a phase transition where if P is bigger than PC, then you have a left to right crossing, and this sort of goes back to Chase and Tourette from the 80s. And so obviously this more recent stuff, which is like a set of thick points. If you just even look at actual thick points on a planar GFF, then it's totally disconnected, which goes back to work of Aru and Ellen and Leonie, right? And then recently it's been proved by Jing, and Zhang, which is that if you look at high enough dimension, then if you take a small enough thickness, you do percolate. Okay? But here we are looking at oriented percolation, directed paths. So that's more special. And so it turns out that although the percolation problem has a phase transition in 2 dimensions, it was proven by Chase in 1995 that in 2 dimensions, for no matter what P is, you never oriented percolate. Somehow the idea is that if you have to percolate, then the path should have somewhat fractal dimension more than 1. Like if you look at a connecting path which survives on this thick point set, then it cannot be just of length n. If it connects 2 points at Euclidean distance n, the path should have at least n to the 1 plus kappa many points for some positive kappa. But because oriented paths only have linear in n many points on them, they're not good candidates to connect 2 points. And so a quantitative version of this was proven by Jing and Zhang, who proved that for any path with a fractal exponent close enough to 1, a good fraction of the points on that path cannot be thick. Okay? But obviously all of this is not refuting still what the passage time is, right? Even if you have 50% of the points which are log n, that can still give you n log n passage time. And yeah, so this is what I just said, so it doesn't improve on the order n log n bound. And so in a forthcoming work with Victor and Kaihao, Jing, who's also one of my students, we show that for all P, LPP and fractal percolation, so you have a path of length n and you want to see how many points from the fractal percolation lives on this path. So that's smaller than n times e power minus c log n by some log factor. So this is a spurious thing, so we expect this to be n to the 1 minus epsilon. So if you do fractal percolation and you do LPP on that and you see how many points can there be on any oriented path. Okay, so this is the result that we proved, but this should be the truth. So it should be the case that it should be polynomially smaller than n. Which if you think of this result as also being true in the thick point setup, then this will indeed improve on your passage time, because it says that the thick points are not going to contribute more than n to the 1 minus epsilon times log n. So all of the contribution is going to come from typical values, which is like no more than root log n. And so you should have like n root log n as your bound. Roughly that should be the thing that you should sort of take from this. But this is the result that we prove. And the log n term, anyhow, so. And again, so the next thing to actually get upper one for the LPP problem is to prove a similar result for the thick points. Okay, so can I go for 1 more minute or 2 more minutes? Okay, so another perspective that I wanted to introduce is, like instead of looking at LPP, which is a 0 temperature model, you are looking at the extremal path. You can also look at positive temperature models, which looks at a Gibbs measure on paths. So instead of looking at the path which is the maximum energy, you look at a Gibbs measure on path where the probability of a path is proportional to exponential of beta times the length. And so beta being infinity is the 0 temperature model, but you can look at a positive temperature presenting model. Okay? And so for i.i.d, like in the sort of KPZ world, so So if you take your temperature sort of correctly as a function of n, this sort of polymer measure is known to converge to some continuum polymer measure, which is known as this continuum directed random polymer, and which has this partition function. So this gives measure as expectation of exponential of the integral of white noise along a Brownian bridge. Okay, obviously none of these things are sort of making sense as is, but you can make sense of that. So there is a scaling limit of the polymer models, and where beta is a parameter, and as beta sort of ranges from 0 to infinity, you get an interpolation between your 0 temperature model and your completely independent Brownian model. Okay? And the partition function is the solution to the stochastic heat equation with multiplicative white noise, and the log of that is the solution of this one-dimensional Kp's equation. Okay, and so you can try to sort of play with this also in the sort of log-related setting. So in an ongoing work with vector, we sort of construct this polymer measure under this sort of GFF-like environment or a log-related environment. And there are various approaches to this. One possible approach that one can adopt is this sort of thinking of this polymer measure as a Gaussian multiplicative chaos in the space of paths, and using that to construct the limiting measure. And so this was done in the KPZ setting by Postel, Ramirez, and Barak a couple of years back. And this can also be, the partition function can be viewed as some putative solution to the stochastic heat equation with log-related multiplicative noise. Although one has to make sense of these objects, but this is sort of a candidate for that. Okay, so let me finish with some broad directions. So obviously obtaining sharp exponents is one. Another question that I quite like, and which is also sort of an important problem in the usual LQG setting, is to understand the weight profile along the geodesic. So you look at the geodesic and you look at the weights on the geodesic, so you can plot the histogram, and you can try to ask what it looks like. So this is the Poisson model. So this is some log plot. So this shows some linear thing, linear decay, which basically means that the contribution is roughly the same from every scale. Okay, this is the BRW picture where you see some positive weights and some negative weights. But anyhow, so the goal is to understand what is the typical weight profile along a geodesic, and the corresponding LQG question is like, what is the typical thickness, let's say, of a point on the geodesic. So these are sort of questions in the same sort of ballpark. Then a couple other things, like you try to construct or make sense of directed Liouville quantum gravity metric. And then the other thing is, so LPP on random surfaces, or what is known as this bulk version of the directed landscape. So this is really sort of directed to experts. So the directed landscape is this construction by Darwin, Ottman, and Virac, which is supposed to be this universal scaling limit of models in the KP's universality class. So it's a model of random geometry. And so it turns out that this directed landscape model is connected to an LPP problem driven by the edge eigenvalues of a random matrix. Okay, this is might not be super familiar to everybody, and this is what is this object called airy line ensemble. So the fluctuation of the edge eigenvalues is given by Tracy-Whelan statistics. Now if you look at bulk eigenvalues of a random matrix, then they fluctuate more like a GFF. And so you can try to speculate whether there is some analogous construction, like whether LPP on a GFF can be made sense of, and can it be connected to some analogous bulk version of the landscape, which has to do with LPP driven by bulk eigenvalues of a matrix. Anyhow, so this is all super speculative at this point, but I'll stop here.